All right, morning nerds. We're going to go ahead and hop over section 6.4 for a little bit. Don't worry, we'll come back to it eventually. I didn't like the order of the chapter because 6.4 was about graphing, and then 6.5 was about more properties of radicals, and I thought since we just did the stuff on that test on all the properties, we might as well just finish off the properties before we do any graphing, things like that. Okay? So today's lesson is just about more properties and more things that can be done with radicals. Specifically, we'll be looking at operations, adding them, subtracting them, dividing, multiplying, things like that. But Mr. M, we kind of already did that already. Well, we kind of did, but when we did it, we were converting them to rational exponents instead of keeping them as radicals. And converting things to rational exponents won't make these things any easier, so we won't do that for these, okay? The first two examples are about addition and subtraction. It's basically combining like terms, because you can only add and subtract radicals if they're exactly the same kind of radical. You treat them as an object. But you don't want to try to combine like terms until everything's completely reduced, so let's go ahead and completely reduce everything we can. These are square roots, so we're looking for perfect squares. The perfect square that goes in, that you can divide by when I say goes in, the perfect square that goes into 45 is, somebody can just shout it out please, 9, great. It's going to leave me 5x. That 5x is going to be stuck in that radical, can't do anything with it. The perfect square that goes into 12, and by go in, I mean divide by, is 4, good. The 3 will be stuck. And then we got this minus 3. And just like the number 12, 4 is the only perfect square that will go into 20. It happens to go in 5x times, and I'm hoping you're already seeing where your like terms are going to be. Now, when a number is sitting next to a radical, it's just like sitting next to a set of parentheses. It means multiplication. So whatever comes out of these radicals will be multiplied to them. So I got the square root of the 9 coming out, but the 5x is stuck inside. I've got the 2 coming out, just sitting right in front of the radical, but the 3 is stuck inside. And I got the square root of 4 coming out. Now you just multiply. 6 and 3 is 18. Three and 2 is 6. And any two radicals that are exactly the same kind of radical are like terms. So these are like terms. Look, I have 18 cookies minus 6 cookies. It's going to leave me 12 cookies. And that's it. Reducing the radicals, combining like terms. Ta-da! I hope you think that's easy. The second example is the same kind of example. The only difference is they're cube roots. So you just need to be able to break down your cube roots. It would be extremely helpful if you knew what your perfect cubes were. As it turns out, 8 is a perfect cube, which means negative 8 is also a perfect cube. You know, in the very first steps, what we're trying to do is reduce anything we can and simplify anything we can. So I'm just going to say this. There's the negative sign. And what's the cube root of negative 8? Shout it. Negative 2. Yeah. Put it in parentheses. That way we know it's actually going to be positive. And now it's time to break, because 192 is not on the list of perfect cubes. Now let's just say you don't know what perfect cube goes into 192. The suggestion would be start dividing by the small ones and see what happens. The smallest perfect cube, positive perfect cube that we care about, is 8. Does 8 go into 192? Sure does. It goes in 24 times, I think. Yes. It goes in 24 times. But here's the thing. 8 also goes into 24. It goes in 3 times. So because 8 can be divided into this and then divided once more, that tells me that 64 goes into this. And 64 is a perfect cube. Don't worry, I won't put numbers that big on your test. because the next test will also have to be no calculator. We already said that 8 goes into 24. Those 3x's are stuck. Yes, sir? Why wasn't this imaginary? It's a good question. It's because it's an odd root. So if you take the number -2 and you raise it to a positive power, that was stupid. If you raise it to an even power, there we go. You're going to have an even number of negative signs which all cancel each other out. So a negative raised to an even power is positive. But a negative raised to an odd power is going to be negative again. So you can take the odd root of negative numbers all day long. They just come out as negative. That is why. If it was square roots, yes, we would have had imaginaries. Or fourth roots, we won't even do in this course, would also create some kind of special imaginaries. But yeah, odd roots of negative numbers are negative. Okay, good question. So we have +2 and 3 times the cube root of 64, which we're supposed to know is 4, cube root of 3x, and minus 4 times the cube root of 8, which we should know is 2. So 2 plus 3 times 4 is 12. I think it's obvious that the cube root of 3x is my like terms. And again, 12 cookies minus 8 cookies is 4 cookies. So reducing and combining like terms. That's all I'm asking you to do. Not too bad, right? I hope. Hardest part about that should have been like a big number. But past that, no big deal, I hope. Fingers crossed. Okay. Cool. Now, multiplying radicals. I got to be honest with you. I think that what I'm about to show you is probably the most difficult thing in the entire chapter. And that's not because the work is difficult. It's because the rules are a little bit wonky. What do I mean? Well, in 6.2 or 6.3, I can't remember, a couple sections ago, we talked about canceling even exponents with even powers. And if the result of that cancellation was an odd power, we had to have absolute value bars. So the rule was, and still is, if you cancel an even exponent with an even root that results in an odd exponent, you have to use absolute value bars. And the whole reason behind that setup was the whole reason that we had to do this was because, well, actually, Jared, you just mentioned imaginary numbers a minute ago, right? We can't take the square root of negative numbers. But every squared number is positive. That means every positive x was acceptable here, and every negative x is acceptable here. That's how we get the plus or minus, basically. So we have to say this. Cool? Okay. But what if I did? Now, you know what? I don't want to bork it up. That's why they were necessary. In this question, odd roots, look, odd roots are our friends. We love odd roots because we never have to think about absolute value bars. The reason why? Odd root of a positive number is positive. Odd root of a negative number is negative. They don't care. Go with that. The domain of an odd root is everything. Plug in whatever you want. No big deal here, okay? So those are our friends. Odd roots are our buddies. When you multiply radicals, you just multiply the radicands. Whatever is underneath the radicals just gets multiplied to each other. Okay? But we're going to think smarter, not harder here. I am not going to do negative 10 times 16. Instead, I'm going to know that I'm going to be hunting for a way to reduce it using fifth roots. And I don't expect you to know right off the top of your head what perfect fifth power goes into this product. So instead, what I'd like to do is, think smarter, not harder. I'm going to break these things down into powers of numbers if possible. All right, well, negative 10 is just negative 2 and 5. Can't do anything with that. And, oh, forgot my 3. Sorry. Get in there, fifth root. Squeeze in there. 16 is a special number, isn't it? What do we know about 16? Come on, guys. You got to help me. The video can't stretch out for eternity while I wait for someone to think. You know. What do we know about the number 16? It's a perfect square. That's something we know. There's one thing we know. What else do we know about it? Not a cube. It's a perfect fourth. It's 2 to the 4th. Why did I write it that way? Because fifth roots cancel fifth powers. And in a moment, we're going to multiply a 2 and a 2 to the 4th. Did you see that? That's going to give me a 2 to the 5th. The 4 and the 3 give you a 12. Now, underneath this radical, I'm going to call it negative 2 to the 5th. I'm cheating a little bit. I guess I should do it like this. How about we do it like this? What is 2 to the 5th power? This is like the 1/5 power I asked you to know. It's 32. So do you mind if we call it negative 32? This negative 2 times this 16, negative 32. Remember why I did that. That's a perfect fifth power. I'm going to be able to take the fifth root of that number. Then I've got this 5 hanging out. Then I got an x squared. I got an x to the 4th. I got a y to the 6th. And I got a y to the 4th. Since they're just multiplying, order of the multiplication doesn't matter. So I clumped the numbers, clumped the x's, clumped the y's. If you have a question about it, ask me, please. Please, please, please. Silence. Okay. Well, then we're going to move on, I guess. I'm going to switch colors. Go Gators. It's looking a little bright, so I'll change over from orange to blue now. I am going to leave it as negative 32 times 5. And I'm going to think smarter, not harder here. We know this is going to make a 6, right? This 2 and this 4. But I can't divide 6 by this 5. Fifth roots cancel fifth powers. So you know what I want to do? I want to borrow one of these x's and scoot it over to these x's. Here's what I just did. Instead of saying, oh, x to the 2 times x to the 4, instead of saying this, I just hopped over this middle ground and said, well, I know I'm looking for things that are fifth powers. So let me borrow one of these x's and stick it on these x's, and now it's a fifth power. Okay? And we could see ahead of the game. 2 and 4 makes 10, and we can divide that by 5, so we might as well just combine them. What that's going to give me is a 5x stuck inside. Everything else will get to come out. So that's going to give me 12 times the fifth root of negative 32. It's negative 2. The fifth root of x to the fifth is x to the 1 because you divide the exponent by the root type. And the fifth root of y10 is y squared, again, because you're dividing the exponent by the root type. Fifth root of 5x. So lastly, just multiply. Yes, what's up? You said why or how? Because it's just the coefficient in the front of the radical. The negative 24. No, again, this is an odd root. Odd roots of negative numbers are negative. Because here, look, if you take the number negative 2 and you raise it to the third power, that means negative 2 times negative 2 times negative 2. What does that get you? Negative 8. That means the third root of negative 8 is negative 2. Just like the fifth root of negative 32 is negative 2. It's because it's an odd root. Only even roots will produce imaginary numbers. Okay. This next question, though, is what I was talking about when I said it's going to kind of monkey with your brain a little bit. The rule hasn't changed. If you cancel an even power with an even root resulting in an odd power, you must use absolute value bars. What we're doing is adding something to the beginning of that rule. And what we're adding to the beginning of that rule is, at the very beginning, decide on the domain of what you're working with. So at the very beginning of this example, I would have looked at this and I would have been like, oh, look, x could have been a positive number or a negative number. It wouldn't have mattered because I would square it, which would give me a positive. But if I had given you this, I'm aware that the x to the third breaks down to x squared times x, and that the square root of x squared comes out as an x. And you might have thought that that means you have to put absolute value bars on this x, but you don't. And here's why. You can only take the square root of positive numbers and 0. But let's just say for the sake of today, you can only take the square root of positive numbers, right? That means in order for this question to be possible, x to the third must be a positive number. And since that's an odd power, the only way you get a positive number is if x was positive. So you'd start by looking at the domain of the original setup. And you go, well, because this is an odd power, and I know I can't take the square root of a negative, that guarantees that x was already positive. So when it comes out, we already know that it had to be positive. Absolute value bars are not necessary. So we're deciding on our domain at the beginning before we do any simplifications. For example, if I gave you this, is this going to result in absolute value bars on my x? No, it is not. Because in order for the entire thing to be possible, x couldn't be negative. So again, absolute value bars wouldn't be required. Are you seeing how that's working? Or no? All right. You guys are just looking at me, so I'll just pretend you get it and move on. All right. So I'm going to look at this and I'm going to see that I have even root, but I have an odd power on this x. That guarantees, no matter what, that x had to be positive. Because if x was negative, this question wouldn't be possible in the real number system. So because I have an odd power underneath this even root, that means the domain of the x's is only positive. So x must be positive. That means it will not need absolute value bars regardless of what happens. Now let's look to our y's. Right here, the y's have an even power. When you go, uh-oh, absolute value bars might be necessary here. Let's look to the rest of the question. Oh, look, this is just a y. So just a y underneath an even root. That guarantees y must be positive. So because of this, x must be positive, and because of this, y must be positive. Regardless of what occurs in our work now, we do not need to use absolute value bars, even if we end up canceling an even power with an even root, because we already know both of these variables must be positive. Yes, Jared? You mean I'm not going to ask you to take the square root of a negative number? I mean, if I ask you to take the square root of a negative number, I expect you to still say I. But for the variables, since we don't know their values, we just go, well, was it an odd root? Okay, life is good. Odd roots, they don't care. Was it an even root? All right, let me look at my exponent now. Was the exponent even or odd? Because if the exponent was even and I had an even root, I'm thinking, absolute value bars are a possibility here. But if the exponent was odd in an even root, that guaranteed that that number, that variable, was a positive number no matter what. Because if it happened to be negative, the question wouldn't be possible. Just like before, we're going to think a little bit smarter before we think harder. I don't want to need to grab a calculator, so I don't want to even think about what 5 times 125 is. Instead, I want you to recognize the number 125 is special. You guys should instantly recognize it as one of the numbers that I told you to memorize. What is it? It's a perfect third power. And was that a hand or a question? So she recognized it. Somebody said perfect third, and she showed me the 5. It's 5 to the third power. So we're going to write this as negative 3. And then we have a fourth root. We have a 5x3, y2. And then I'm going to say this is 5 to the third, x2, y. This time I showed you I multiplied them, and now I'm going to reorder them. You see, it doesn't matter. Multiply and then reorder as you multiply. It doesn't matter. It doesn't matter. This is going to give me a 5 to the fourth power. You don't even know what it is. And look at your x's. Again, fourth roots cancel fourth powers. So if this x were to steal one from here, instead of saying x to the third times x to the second, I could say x to the fourth times x. But your y's, there's only 3 of them. So no matter what, they're stuck inside. These two things are stuck. The 5 comes out, fourth root canceling the fourth power. The x comes out, fourth root canceling the fourth power. Mr. M, does it need absolute value bars? No, it doesn't. Because we already know x had to be positive. So it doesn't need absolute value bars. And then you just say negative 3 times 5 is negative 15. So if you have questions about what ifs or why didn't you use or anything like that involving multiplying radicals, specifically, well, not specifically, but importantly, understanding when and when not to use. Yeah, when and when not to use absolute value bars. Let me hear it. Yes, Donald. I just forgot to write the stinking 2. Why'd you wait till now? All right, well, luckily I can fix that. There. Just forgot that turd. And these people watching the video for the first time and be like, where's the 2? Where's the 2? Where's the 2? And at the very end, they're going to be like, oh, you forgot the 2. Okay. Any questions about the absolute value stuff, the exponent stuff, the radical stuff? Yes, Jared. This 2. I just forgot to keep it.
And also, why wouldn't, like you said, it won't be possible with the y with negative?
in the real number system because it would be imaginary. If y was negative, the fourth root of a negative number is it's a type of imaginary. There's actually 4 of them. But the point is it's imaginary. So we can't do it in the real number system. It's not possible in the real number system. Why don't you ask me, that way it can make its way onto the video? Yes?
Are we ever going to like the final product, are we going to have to use imaginary? Are we going to have to use I?
The only time you'd have to use I and an end product is if I asked you to take a square root of a negative number. But it wouldn't be a variable. It would be a number specifically. Okay? Functions of complex variables is the hardest math I've ever learned in my life. I barely escaped with a passing grade. I wouldn't ask you to do it. Kelsey, you seem to be asking Donald a question. Is everything good? Okay. All right, moving on then. Scoot-oop. Guess what? You could distribute, not complex, you could distribute radical numbers as well. We're going to find the area of this pennant, Go Gators. First, do you guys remember the area of a triangle formula? 1/2 base times height. This is great YouTube content. No class talking to each other, won't talk to me. This is awesome. This is your base. This is your height. You don't have to, but I strongly suggest that you reduce all of your radicals before you start multiplying. Why? Because you want your numbers to stay small. That's why. The square root of 8 reduces. To 2 root 2. But you should already know that, though. So if I'm multiplying this 3 to a 2 root 2, it gives me a 6 root 2. And if I'm multiplying this 7 to a 2 root 2, it gives me 14 root 2. Like that. Because 8 is 2 root 2. 3 times 2, root 2, 6 root 2. Because 8 is 2 root 2. 7 times 2, root 2, 14 root 2. Okay. And you're just going to do something that you know and love. Distribution. Yay. Wow, go home. Distribution, you're drunk. There we go. And I'm going to worry about that 1/2 at the end. For now, I'm just going to bring it along. 6 times 14, I don't expect you to know it off the top of your head, but 6 times 10 is 60, and 6 times 4 is 24. 16 and 24 makes 84. What's root 2 times root 2? It's 2. Because you just squared a square root. You call it root 4 if you want to. But what's the square root of 4? It's 2. There you go. 6 root 2 times 6 root 3 is 36 root 6. Again, do you know 4 times 14 off the top of your head? Probably not. But 4 times 10 is 40, and 4 times 4 is 16. 40 and 16 makes 56. And 4 times 6 is 24. Now I'm going to distribute my 1/2. When I distribute here, the 1/2 and the 2 will cancel each other. So it'll leave me 84. Half of 36 is 18. Half of 56 is 28. Half of 24 is 12. And that's it. That's the area of that pennant. Whatever that number is. No, because 6 can't be divided by a perfect square. These are not like terms. So there's no like terms here. That's it. It's finished. Good stretch, good stretch. We good to flip? Okay. In the essence of time, I'm going to skip the next question because it's literally just multiplying those two irrational numbers. It's the exact same question. Even easier though, because we don't have to divide by 2. So we're just going to skip over it because I want to get to this. Rationalizing denominators. Technically, you shouldn't let radicals be in the bottoms of fractions. I mean, the higher you go in mathematics, the less they care. But this is one of those things where we're like, you're not supposed to have improper fractions. Okay, well, you're not supposed to have radicals in the bottom. So at least I'm going to show you how to manipulate it to make it so there's not radicals in the bottom. When you get into future mathematics, your teachers are going to be like, hey, remember that thing about no radicals in the bottom? Screw it. Keep the radicals in the bottom. It makes your life easier. But for now, we're going to learn how to at least handle it. Right now, there's a square root in the bottom of my fraction. I can't have a square root there. How do we normally get rid of square roots? Squaring. But you are not allowed to square the top and bottom of a fraction. It changes the value of the fraction. For example, if I told you your fraction was 1 over 2, could you multiply the top and bottom by one number and keep the same value? Of course. If you wanted to multiply by 4 over 4, you'd get 4 over 8, which is still 1/2. The reason why that works is because 4 over 4 is 1. But if you square the top and the bottom, you get 1 over 4. And these two fractions are not equal. So you're not allowed to square the bottom of the fraction. But I kind of already gave it away. What are you allowed to do to the top and bottom? You can multiply. So what could I multiply by to give me the same result as squaring that root 6? I could multiply by the square root of 6. So I can multiply by the square root of 6 on the top and bottom because that will give me the same result as squaring the bottom. What this is going to give you is a 2 root 6 over 6, which reduces to root 6 over 3. And it's finished. So the square root of 6 over 3 is the same as 2 over the square root of 6. How did what turn to the square root of 6? How did the 6 turn into this 3? Yeah, I just reduced. The 2 over 6 reduced to 1 over 3. What's confusing? Somebody just whispered, this is confusing in the back.
It's easy to do. It's just like confusing to get. I don't know.
What part?
I don't know. It's easy. It's just like confusing because it's more. Like more stuff.
I want to help, but I don't know what you don't know. Okay. Let's try the next one. You're maybe thinking to yourself, oh, true, that's easy. I'll just multiply the top and bottom by the cube root of 4. Yeah, that's not going to work. And here's why. The cube root of 4 times the cube root of 4 is the cube root of 16, correct? Is 16 a perfect cube? No, 16 is not a perfect cube. So multiplying the top and bottom by the cube root of 4 will not work because it's still going to leave a radical in the bottom of the fraction. What do cube roots cancel? Third powers? Yeah. Cube roots cancel third powers. You know what's special about the number 4? It's a square. Third roots cancel third powers. That's almost a third power. If only it had one more 2 down there, right? If there was one more 2, it would be a third power. So let's multiply the top and bottom by one more cube root of 2. Because if you do that, you get 8 times the cube root of 2 over the cube root of 2 cubed. And the cube root and the cube cancel each other and leave you with just a 2. And 8 divided by 2 is 4. Cube roots cancel third powers. 4 happens to be a second power. We just needed one more 2 underneath that radical to satisfy the radical. So we gave it one more. But whatever we do to the bottom, we have to do the top. There should probably be some questions about that, and I would love to answer them. Yeah. So why couldn't you, when you say cube them, you can't raise tops and bottoms of fractions to powers. You can never do that. Something you could have done, which is working harder than you need to, you could have said there's a single 4 here, so why not do the cube root of 16 on the top and bottom? You could have done that. The problem is your cube root of 16 on the top would have reduced because 16 contains an 8. So you're always trying to figure out if something is already a power or not. Cool? Let's reduce. Unfortunately, 32 over 3 doesn't reduce. But x over x squared, or x a third, gives me 1 over x squared. Even root, even power, bells and whistles screaming at you, alarms going off. Decide your domain. Since it's even root and even power, could x be positive and negative, and you wouldn't know? Yeah, it would be, because if you raise that negative number to a positive, or to an even, you're going to get a positive regardless. That means when I'm finished here, I'm probably going to have some absolute value bars. The root of a top and bottom of a root of a fraction is the same as saying root of top, root of bottom. And a moment ago, Melissa, you were whispering the numbers that I want to break 32 into. And you said 16 times 2, because 16 is a perfect fourth power. All this is simplifying before we even attempt to rationalize. There it is. Okay. I need you to see that 3 is just 3, so it's 3 power 1. X is just x, so it's x power 1. Fourth roots cancel fourth powers. Yep. I just lost my exponent, you mean? Yep. Catch. Thanks. It was, but x over x to the third reduces to 1 over x squared. Remember, when you divide two numbers the same base, you subtract the exponents? Fourth roots cancel fourth powers. How many more 3's am I going to need under there? 3 more 3's. How many more x's will I need? 2 of them. 3 more 3's, 2 more x's. Come on. Okay, we'll say it again. Fourth roots cancel fourth powers. How many more 3's do I need? There's 1 here. How many more do I need? Oh my God. Okay, let's try this one more time. Fourth roots cancel fourth powers. This is a first power. How many more? 3 more. There's the 3 more. On the bottom, I'm going to have my 3 to the 4th that I needed. On the bottom, I'm going to have my x to the 4th that I needed. That means I had an x to the 4th inside a 4th root. But since we decided at the very beginning that x could have been positive or negative, we have to have absolute value bars down there. On top, 2 times 3 to the 3rd, that's 2 times 27, that's just 54. Can't do anything with it, and then there's an x squared. So there's 2, 4th root of 54x squared. We'll have to skip over the last one. I have to move on. You have to see the next example. Luckily, you've already seen something like this before. Conjugates. Anytime you multiply 2 conjugates, you square the front, square the back, put a minus sign in between. We've actually done this before. This is irrational conjugates. Great thing about irrational conjugates is it doesn't even matter what order they're written in. All you do, if you're trying to rationalize the denominator that has an irrational number in it with plus or minus, is multiply by the conjugate. Switch the symbol between them. That's all you have to do. So you're multiplying by 2 root 6 plus 3 on the top and bottom. On top, you just distribute. That's easy. And on bottom, square the front, square the back, put a minus sign in between. On the bottom, square the front, square the back, put a minus sign in between. On top, distribute. Easy peasy lemon squeezy. You are squaring this 2 to get you 4, and you're squaring this root 6 to get you 6. That's 24 minus 6. It's 15. Woo. Isn't that fun?